I'm going to demonstrate how to use an interactive simulation that models a heat exchanger, in this case, a heat exchanger in which fluid flows to the center of a concentric tube and another fluid flows through the annular region. And the figure here is for parallel flow. So the hot fluid is flowing in the annular region and the cold fluid is flowing through the center of the tube. The simulation is located here, and then I'm showing a snapshot of what the temperature profiles look like for this parallel flow arrangement. And so the hot fluid temperature decreases, cold fluid temperature increases, that objective of the heat exchanger. We can change the flow rates of each of these with sliders. We can also change the length of the heat exchanger, and we have three choices for the hot fluid. The cold fluid is fixed as liquid water, but we can change the hot fluid. We can also change the flow rate. I'm showing parallel flow, but we can also have counterflow in which the cold fluid flows in one direction and hot fluid flows in the opposite direction. So let's look at this simulation, better understand the processes. So here we're looking at the simulation. Let me point out that the details have the equations that are used to generate the temperature profiles. We're also calculating the heat transfer rate, which is indicated here. And we can switch over to countercurrent flow. And for example, we can change the mass flow rate of the hot fluid. As we do that, we see the temperature, of course, doesn't change as much and make it more dramatic. If we slow down the mass flow rate of the cold fluid, so then there's a large temperature change for the cold fluid compared to the hot fluid. Can make the heat exchanger longer. Then you see we get more heat transfer, obviously. The fluid, instead of liquid water, for the annular region, we can have air. Of course, air doesn't have the same heat capacity, and so we get a much bigger temperature change for air. Or we can use liquid sodium. Observe, of course, there's a pretty big temperature change, but the heat transfer rate, if we compare liquid sodium to air, see a difference in heat transfer rates. So part of its objective here is to understand, for example, the difference between countercurrent flow and the parallel flow. As, of course, the hot and cold fluids approach each other in temperature, then there's not much heat transfer. And so the heat transfer rate, if we look at that 26.4, and it's larger here for the countercurrent flow because we have larger temperature differences.